things more along these lines. How many of you would be excited about drawing that in your notes? Why not? It's a lot to draw, and particularly for those of you typing, that's going to be really hard to type up. So what might we do as a way to simplify that, say, for this class, that still gets some of that information but makes it easier to type? What could we do?
Nomenclature.
What was the suggestion?
Nomenclature.
Nomenclature, not quite, but right idea.
Or something like that.
Get better technology, so we could take it as to writing technologies. We could get a better technology that would allow us to draw it easier. How many carbons are in that structure? 8. How many hydrogens? 10. Oxygens? Nitrogens? 4. So we could write out a chemical formula to condense that structural information into something that's easier for us to type up. Right? That removes the relative position of those things. So that could lose a lot of information about the chemical identity of that molecule, and I would agree. I think it completely removes that, and I think we shouldn't be using chemical formulas. However, as you all just noted with the initial question, you don't want to draw out the structure, you wanted to draw out the formulas. The formula retains some of that information, and it simplifies our interpretation of the structure. Okay? The problem with that formula is that there's a variety of ways that I could arrange the elements in that formula to different structures. Right? And that's where the problem lies. So depending on what information we're trying to encode, we may want to use a full structure or we may want to use formulas. For the sake of this class, what do we use? Formulas. Right? We talk about Lewis structure, but it's pretty much here it is, and then we move on and just look at formulas. So pretty much for the rest of the semester, we'll be looking at just our formulas and using that information to code certain things. Okay? We've already coded certain pieces of information into that formula. What did we code in it? What amount?
The amount of each element.
Yeah. I know there's 8 carbons because there's an 8 right there. Okay? And that applies to the carbon. What does it not apply to?
Everything else.
Doesn't apply to the hydrogen, the oxygen, or the nitrogen. Okay? So the location of that information gives me information about the amount of each of those things in that formula. And while this may seem like a simple observation, it is a critically huge observation that most students forget about by the end of the semester. Right? And we end up having to rediscuss it. Okay? So remember what your formula shows you. It tells you the amount of each of those pieces that are there. Okay? So we could go through and look at other formulas. H2O, C6H6O6. Okay? When we see H2O, almost everybody jumps all over water. Why do we immediately jump to water and not say some other compound?
Because we know that that's
There's only one way you can arrange the atoms of 2 H's and 1 oxygen. That one way results in water. Okay? But C6H6O6, that's a little bit harder. Okay? But it at least follows that same pattern. We group the elements, we put a number next to them to specify how much, and we're all's good. What happens with HC2, H3O2? Anybody notice anything weird or bizarre about that one?
That's a ternary oxyacid, isn't it?
Why are you now saying it's a ternary oxyacid all of a sudden?
It starts with a hydrogen and it has an oxygen and 2 nitrogens.
You're noting that it starts with the hydrogen. Okay, why is that different than the previous cases? Said another way, why did I not write this C2H4O2? I'm trying to draw attention to the chemistry of that structure. Okay? And one of the things that we expect you to learn is by looking at that formula, some information can be pulled from it. If there's a hydrogen out front, that is one of our red flags that we have an acid. Why might I want to call attention to the fact that I have an acid?
They're dangerous.
They're dangerous. Okay? So if I can tweak and code some of that information in that formula, that can help me understand something about their reactivity and it becomes useful. What happens with C2H5OH? Is that coded differently? Okay, why is that one coded differently? Okay. And I would step away from the statement of OH. Why is this one different than C6H6O6? It pulled the hydrogen out of the formula. Instead of saying C2H6O, we said C2H5OH. Why are we doing that?
Draw attention to the chemistry.
We're trying to, again, draw attention to that hydrogen. And in particular, we're trying to draw attention to where that hydrogen is connected. In the formula C6H6O6, I know nothing about how they're connected. Just like when I looked at the formula for the big structure in the middle. All we did was just simplify down. I can go through and draw attention to the chemistry of the structure. Holy crap, that's dangerous because it's an acid. Right? I can also draw attention to the connectivity of the atoms. Where do you think that hydrogen is connected in this structure?
To the oxygen.
To the oxygen. It's a simple visual cue about how we're organizing our formulas to draw attention to some structural or chemical features.
Would that be a base?
No. Okay. And I know exactly why you want to call it a base, and it's one of the biggest common misconceptions in chemistry. It usually bugs the crap out of me in OChem. We'll talk about that, believe it or not, at the very end of the semester, what's being referenced there. Okay. I know what you're getting at, but it's beyond the scope right now. Okay. We could also go through and switch things up. For instance, if we go through and look at the next formula down, does that formula look familiar at all to anybody?
This is CO2.
Well, there's interesting. There's a CO2 sitting in the middle of that. There's a CH3. How many carbons are in this? 2. How many hydrogens? 4. How many oxygens? Guess what this compound is? Same thing as the one above it. Exact same compound. Why did we change the formula around? Goes back to our structural aspects. That formula switch of those sequences of letters ties information to structure. The HC2H3O2 that was drawn above really doesn't call any aspect of structure. What this is calling out is really an aspect of chemistry. Okay? And ultimately, not even chemistry, because really we're saying it's an acid. By writing that notation, we're actually not really calling so much attention to chemistry, but really saying danger. Why use the notation down below? Well, the one below it draws more attention to the structure or the connectivity of each of those atoms. Okay? How do those pieces come together? Okay? So what I want you to be aware of is that our formulas can change, and depending on the context or the level of chemistry you're at, you may see formulas kind of swap around and change their information. Okay? At their core, they mean the same thing. Okay? That subscript 3 next to that hydrogen means there's 3 of that type of hydrogen. There also happens to be another one. Okay? So the formula can code for a lot of information depending on how we want to format it.
And it's actually more of a language thing than anything else, because these are synonyms of each other. They mean the exact same thing, but in different contexts and with different rhetorical purposes. You use one over the other. It's the same thing as saying someone's less knowledgeable versus calling them an idiot. In some contexts, calling someone an idiot works. Some contexts, you need to say that they're less knowledgeable.
So when you said those are different, that's one type of hydrogen, would the second hydrogen be an isotope?
No, it's a different reactivity. An isotope does have different reactivities. Typically, we wouldn't actually call it like... Mother F. They did this morning, too. I got in trouble for leaving it unplugged, so I have to make sure it's like a mess up here, so I remember to plug it back in. Sorry. What were we talking about? Oh, the different forms. Okay? This hydrogen, the one at the tail end, is actually acidic. Okay, that is an acidic hydrogen. That is the same one as we put out front. Why did we change the location? Because if we flop the order around, structurally it makes less sense when we try and put it together. Okay? Which at this stage you're probably like, that makes no sense to me, because you aren't used to those structural patterns. You aren't used to the sociocultural conventions for how we put those formulas together. Okay? But it gives more information about the structure. So its reactivity is different. That hydrogen is acidic. That's the one that melts your face. The H3, those hydrogens have virtually no chemical reactivity. Okay? So we're kind of separating them to enhance our visual cues for what that chemistry might be. Okay? After that, we could also go through and shift into chemical equations. Okay? And the chemical equation is doing much the same thing, but now we're layering more information in. Instead of being a single molecule, we have 2 molecules or 3 molecules. Okay? And those are effectively math expressions. 1 plus 2 equals 3. Okay? So the part that's tricky is that we are now doing math expressions with the alphabet. Okay? And not really the alphabet, but elements and atoms. And it's our symbology for those elements and atoms that makes it a little bit trickier to deal with. So we have to deal with that interpretation and make sure we understand what those formulas mean, so that when we move them into the secondary context of the math expression, or now the chemical expression, we can understand what they mean and why and how it's happening. How to make sense? Okay. So that's kind of our summary of our Unit 1. We looked at all the atoms, right? We looked at how we could arrange those into structures. We now can arrange those into formulas. To reference those, we might want to call attention to their reactivity, so we could change the order of our atoms in our formula. We might also want to be able to name these things. Right? Because if I stand up here and I'm sure if a chemist listened to this video and heard me reference HC2H3O2, they would start screaming, okay, at the computer screen, because no chemist would refer to it by the formula. Okay, what we would refer to it by is the name of the compound. It's not hydrochloric acid, okay, but we would go to the name. How do we know how to name it? Well, we would have to have a logical rule system that establishes those names. And for those of you thinking that nomenclature within chemistry is a pain and difficult, imagine if we used the same nomenclature system we use to name babies. Think about that one for a second. Why am I called Mike?
That's what your mom said.
That's what my mom said. So I found the new compound of 2 hydrogens bound to each other. You're Bob. Okay? You're Hippoflabodopotus. Okay? There's no logic behind that naming system. It's kind of random and arbitrary. What sounds good to your parents or the creator? When we deal with the nomenclature system in chemistry, we've created those categories to very intentionally allow us to consistently come to the same name regardless of background. Okay? That anybody was able to do that is phenomenally amazing. Okay? And for those of you that even question that, consider everybody's name in the classroom. And then for the next thing, consider the distance between the front board to the back board. What is that distance?
25.
25 feet. Anybody else want to hazard a guess?
Like 15 feet.
15 feet?
26 feet.
26 feet? We're literally looking at the same distance and we just got 3 different numbers. And I would argue we haven't even scratched the surface on the complexity of this problem. 6'4". Interesting. Am I 64 feet? What did you not suggest as a unit for measuring this distance? Inches. Okay? Or centimeters. Or millimeters. Or meters. Or miles. we're still looking at the exact same distance, and yet depending on the unit system we choose, we could get entirely different numerical values. Okay? You think, well, but scientists are clean and easy. Look at distance. Again, inches, feet, okay, versus centimeters, meters. Okay? We don't use the same unit systems, and that is arguably a really easy thing to agree on. And yet somehow we're actually able to get together and agree on how to name compounds. Okay? And pretty darn consistent. Okay? So nomenclature as a class has some pretty impressive science and agreement behind it. Doesn't mean you like it, doesn't mean I like it, but it's good. Okay? So let's skip to that kind of front board to backboard thing. What we're looking at now is the PSS chapter, which should largely be a review based off of the stuff you've seen and done in lab. Okay? So if at any point you're like, I got a question about that, you need to stop me, because what I'm planning on doing is moving through this section very, very fast. Everybody understand that? Okay. So, measurements. Okay. So, in that measurement from front board to backboard, it was good. We had 3 measurements shouted out, and in their measurements, they all provided the unit. Okay. So, when we take any measurement in this class, it is not 25. Okay. It's not 15. It's 25 feet, 15 inches. You must include that measurement unit. Okay, that measurement unit is critical. When we're talking about what types of measurements we can make, there's 4 primary categories that at least the PSS chapter decides to address. There's a 5th one not up here, which we'll address in a second. Distance or length. What unit would we use for distance or length?
Metric system.
We probably want to use the metric system. Okay? We have feet, inches, miles, or meters, kilometers, centimeters. Why would we pick one system over another?
Because everybody else uses the metric system.
Because enough people got together and said, this system works for me. Okay? Any ideas why we might pick the metric system over the imperial system?
Easier to convert.
You can get smaller units.
Inches to feet is equally universal as centimeters to meters. Doesn't mean it doesn't exist. Whoops.
Oh, the metric system's all tens.
Metric system is powers of 10. If we look at the imperial system, what are our powers? How are we shifting units? Well, powers of 12. Okay, fine. Powers of 12. 3 is not a power of 12. Okay? Take it the next step. Okay? After yards, we'd move up to miles. How many feet are in a mile? 5,280. Okay? There's a stupid internet meme about tomatoes and how that's supposed to help you remember that it's 5,280. Okay? The metric system is a lot easier because they go by powers of 10. Why? And you're wondering about the tomato reference? I don't remember it, so sorry. The metric system. Why might the metric system be nice by powers of 10?
1,000 meters, 1 kilometer, not 1,200
I can give you 10 reasons. We have 10 fingers. Those are easy multiples to work with. Okay? Why is 12 inches a weird system? To measure 12 inches, I have to take off a shoe. Okay? Maybe in the old days that's not a bad idea because we didn't have shoes. Maybe we should go, oh, see, it's 12. Okay? See, 12. Okay? That's a bit of a silly system to work with. Okay? So when we're thinking about our distances and lengths, and for that matter, mass, volume, and time, we want a consistent measurement system. Okay? These are all arbitrary human inventions that we got together and agreed upon to say was the best way to evaluate this. Okay, so for distance and length, our primary unit is meters. Okay, we're looking at the metric system. We can go powers of 10. Mass or weight? Grams, which is a fun one historically because our standard unit for mass is actually not grams. It's kilograms. Okay. That said, I will always reference it as grams because it makes more sense in that system. Volume, liters, time, seconds. Why not minutes?
Is it on millimeter?
We can still do milliminutes.
That big?
Yep.
It's too large of a measurement.
We're looking at chemical reactions. If you walked into the chemistry lab and each of the labs took 24 hours because our reactions ran on the scale of hours, how many people would join chemistry? Not very many. Okay. I'm not saying we designed chemistry to go faster than that, okay? But chemistry on its own tends to go faster than that. We tend to run on the second time scale. So when we're looking at our primary units, those are the unit systems that we tend to use. Does anybody want to write out meters, grams, and all of that? No. So what do we use? M, G, L, and S. Yeah?
What kind of writing system is that?
What the letter represents the word? I forget what it is.
I can take logographic or I would take phonetic.
That's a good exam question. Just saying. Mass measurements, yay! We can take mass using balances. We almost always use a digital balance. This is a cool little link. I think it's neat if you go out and click it. We're not going to click it and watch it, but there's a guy that gets more excited than I do about chemistry, and in particular more excited about mass than I do. Okay? So it is kind of neat. I'd recommend it if you want to go out and take a look. Volume measurements. Okay? Why do we need a new system? Why don't we just use mass for everything? What would we measure with mass? What kind of state of matter? Probably solids. Why solids? You just put it on there and you can balance it out. Okay? Why invent volume measurement systems?
For irregularly shaped objects.
For irregularly shaped objects, but I can still get the mass of an irregularly shaped object.
Once they don't balance, it's gonna go.
So it's not the shape of the object that's important, it's the, begins with a P, phase. Okay? Why do I want a volume measurement? Because one of my primary phases is liquids. It's not easy to get the mass of a liquid because I need a secondary container to hold it. Okay? If I'm going to use a secondary container, I might as well just put markings on the secondary container and establish a volume measurement. Okay? So our volumes are primarily for liquids. Variety of different devices do that. Yippee. Measurements and uncertainty. Okay? This is what we talked about in lab. Whenever we take a measurement, we have to report all of the obvious digits, and then we have to guess one more decimal place. So the length of this rod would become 4.2. Anybody else? So everybody just nodding agreement? Okay. So we have 4.2, 4.2, 4.2. Greg, you want to help me out?
4.27, except that you say plus one guess, so 4.1.
Thank you. Okay. So when we talked about this in lab, we send this out for everybody to go through and measure. We make the assumption that everybody knows how to make that measurement, okay, which we have to be trained in, clearly. Okay. Once we've done that, we can go back now and take the average of all of those and see what the average is. Once I have the average, I can see the standard deviation. How much did each of those numbers differ by from the average? That difference is the precision of the device. And it turns out that that precision of the device will always change where? In the guess decimal. Okay? Your precision of the device should never change in the exact value, okay, or the obvious digit. Kind of make sense? Okay. How do we get more sig figs? my device has to have more refined measurements. Okay? So, significant digits. Okay? So let's take a look at, should we try those as an example? Let's try those. Sig figs, first number.
2.
1. Second number. 2. Third. 3. Fourth. Last one. 1. Ouch! Okay.
It wasn't just me, yes.
Digits 1 through 9 are always significant. So when we go through these, we could go through and underline each of the digits that's 1 through 9. So all of them have at least one sig fig. How did we dictate whether we had more or less sig figs, or sorry, more sig figs than that?
Decimal points.
It all had to do with labeling what? The 0 as significant or not. Deciding on if the 0 is significant all comes down to the explicit statement of the decimal point. If the decimal point is not explicitly stated, that changes the meaning of the zeros. In our very first number, what is that numerical value? 10. Good. Okay. That as a measurement is not actually 10. It is the number between 10 and 19. I said, well, that doesn't make any sense. By not including the decimal point, that 0 is only a placeholder. Meaning the 1 needs to be placed not in the 1's place. Which means if I look at that as a measurement, as a number scale, okay, the 1 is not allowed in the decimal or in the 1's place. Okay? Because there's an implied decimal, I know that that's where my number starts, the 1s. Okay? Where does the 1 belong? In the 10's place. Okay? So the number I've reported is just 1 in the 10's place. I have reported no information about the 1's place. Okay? That means that could be a 0. It could also be a 9. Okay? If I write it out with the number line, as it's shown here, does that make it a little bit more obvious what the meaning is? Yeah. So why do we have these decimal sig fig rules? Why don't I just show a number line? Okay. I've got a bunch of numbers that were empty before, a bunch of number lines that were empty afterwards. Okay. What is the largest number we could go to? Infinity. What's the smallest number we could go to?
0.
Negative infinity.
Negative infinity. Okay? Which means I could draw number lines forever and still not cover all of the number places. Okay? To write number lines without ever taking a measurement, okay, is a pretty silly lifestyle. Okay? So we had to come up with the sig fig rules to help us identify when a 0 was a placeholder versus a decimal point. When we move to the next one, why is that one now 2 sig figs? Because of the decimal point. The explicit statement of the decimal point means the number that shows up in the 1's place is 0. Now I'm looking at the number exactly 10, or not exactly, but 10, not the number between 10 and 19. So I get 2 sig figs. What happens with the next one?
Third 0
I get a
becomes a sig fig.
third 0 becomes a sig fig. And so what we're trying to do is develop a system that allows us to differentiate that. That system is the rule set that you saw in class or in lab. If there is no decimal point, the 0 must be controlled by numbers to the left and right, at any place to the left and right. Okay? If there is a decimal point, then the 0 needs to be immediately preceded by a significant digit to be significant. 102, how many sig figs? 3. There's no decimal point, which means the 0 has to be bound by sig figs. To the left, there's a 1. To the right, there's a 2. Both of those are sig figs, which makes the 0 significant. Next one. Next one. Next one. Sorry, Nick. Shh. Next one. Next one. Next one. Next one. Why is the last one 3, not 2? Okay. The 1 and the 2 are significant digits. I look to the left for the 0. What do I have? Nothing. Look to the left. Not a significant 0. I look to the left. A significant digit. There's my 3 sig figs. Top number versus the one right below it. Why show those? What's the difference between those two numbers? There's a 0. Does that affect the number? No. Why put those two up there? I'm going to take a measurement. Take a guess as to what I measured.
The height of Molly.
Height of Molly. Really? Molly is only 6 inches tall? What? What do you mean? Well, let's... Oh, you jerk. I pushed the wrong button. Let's try that again. Did I write 5 feet? You want to tell me what that is right there? That's not blank. Those are the really good eyes. That's a decimal point. Okay. How do we make decimal points? You usually punch the paper, right? If you punch the paper but the lead or the pen didn't transfer very much, what do you see? At best, a faded dot, which means if you're on a test exam and you're running through this calculation really fast, you just measured the height of Molly and said she was only 6 inches tall, or half a foot. If instead you had said this, you might have been, why did I put a 0 there? Oh, I didn't draw that decimal point quite dark enough. There's a decimal point, that's only half a foot. That's a leading 0. The only reason it's there is to call attention to the fact that you did draw a decimal point. Okay? Again, this is one of those simple things you're like, that's not that big a deal. It's a really big deal because Molly just grew 4.5 feet, okay, in seconds. Okay? So we want to be careful to watch out for that decimal point. It can be a really big deal. Okay? This is a fun one, measurement versus exact. How many quarters are in that image? 7. I like it. That's good. How many sig figs in that measurement? 1. So if there's 1 sig fig, you're saying there could actually be 7.1. Could there be 7.1 quarters in that image?
Yes.
How many of you think you can have 0.1 of a quarter?
You should cut it.
No. It's not a quarter anymore. Go to the bank. Try and give it to the bank. They won't accept it.
Probably need 0.6 of a quarter for them to accept it, right?
Okay, you probably need 0.6 of a quarter to accept it. So 0.1 doesn't work. Okay, so it's not 7 quarters. 7.0 then, right? So then it could be 7.09 quarters. No, okay, well, so then you're saying it's 7.00 quarters. 7.009 quarters? No. I'd have to put zeros forever after this measurement, which means when I take the measurement 7 quarters, how many sig figs? If it's 1, you're telling me 7.1 is a valid answer. There's an infinite amount of sig figs. An exact measurement has infinite sig figs. This usually works really well for when we're counting things, and typically counting small amounts of things. Okay? If we count probably less than 100, we're probably somewhat decent at being able to do that, and that measurement is infinite sig figs. What if I count a billion individual things? What are the odds I'm going to get that perfectly correct? Slim, which means there's an error in that measurement. That measurement is now going to carry some sig figs with it. Okay? It won't be exact. Okay? Where this shows up most often is actually in other statements. Not so much a measurement, or a counting. There are 12 inches in 1 foot. How many sig figs? It is infinite, because it's not 12.1 inches in a foot. It's not 12 inches in 1.1 feet. There are exactly 12 inches in exactly 1 foot. That measurement, or that definition, has infinite sig figs. Okay? And it does not affect the sig figs in your calculation. Which gets us to the next part on this. Why do we worry about sig figs? When I go through and do mathematical operations, the sig figs have an effect on the answer that I get. So if I went through to attempt this addition, okay, I think I can pull this off pretty quickly, so let's give it a shot. I think we're looking at... Anybody want to check that for me? Did I do that right?
Looks right.
Okay, good. If I asked you to do that addition and you wrote that answer on your test, you're wrong. Why? Nope, I'm fine with the work. If that's what you say the answer is, you are making a really big assumption. What is that assumption you are making?
You're assuming the sig figs.
0, 0, 0, 0. Is that true? No. We have no information about those zeros. What could they have been? They could have been 9s. Okay? So if I went through and did that math, and I forgot that I have to do all this addition in this class. Okay, I think 115.7346. The other one, we get that one up there. 16362. Can I get a confirmation I do those right?
You don't have 5 digits on the bottom.
What was that?
You don't have enough digits on the bottom.
1, 2. Oh, that's even more fun. Probably because there's a 0. Oh, there aren't. I don't even know how I pulled that one off. Okay, so someone needs to learn to use their calculator more appropriately. Apparently that's me. What is the difference between those numbers? Where do they differ? In the tenths place. Let's take a look at our addition-subtraction rule. Our addition-subtraction rule. Our answer is only as precise as the least precise measurement. Which of these 3 measurements is the least precise?
First one.
The first one. It only reports out to the tenths place. If we go back to the calculation, where did we run into an issue? In the tenths place. The rule, our sig fig rule for addition-subtraction, took into consideration what happens when we make the opposite assumption of them being 0s versus 9s. That's where the difference falls. You are responsible for knowing that rule whenever you do addition and subtraction. Okay? So what is the correct answer for this? 115.6 grams. Every other answer is wrong. Okay? Those of you saying, well, the calculator told me something different. You're right. The calculator assumes that everything was exactly true. It's not exactly true. Measurements are things the calculator has not yet caught up with as far as doing mathematical operations. So you have to deal with sig figs appropriately. But at least there's only one rule.
How did you round up that this 7 plus 3 plus 5 is 15? So how did you get 115.6? Do you have to round that tenths place? Because there are sig figs behind.
It's the answer he got, but it would show it to as.
So you said 7 plus 3 plus 5 is 15, but remember when you carry 8 and 5? 8 plus 5 is 13, you carry the 1.
You can add that 0 as a guess? Or, because,
So when we go through to run the calculation, we make the assumption that they're all zeros, and we still total up exactly as it reports out. Okay. When we do that, why did the 7 plus, or the 3, 7, oh, never mind, I see what you're saying. Okay. So what you're saying is then this should be my calculation.
Yes.
No. Why is that not your calculation? The other ones have information in them. I know information about some of those places. By deleting that information, I'm removing information from my calculation.
So,
Okay? So that stuff still has to get factored into the calculation. And I run the calculation assuming those are zeros. I just make sure that the rounding effect of those affects out with that place. Does that kind of make sense? Those extra data can give me that a minimal value.
okay.
Okay. So ultimately, when you apply your addition subtraction rules, it is only at the end of the calculation. You never do it partway through. Multiplication division. What is the area of a square?
Square.
Yep. Or a rectangle, whatever.
Like the formula?
Yeah, how do you do it? Length times width times height would be for a cube thing. We just have length times width. 7.28 units times 4.6 units. What do we get? Okay, if I did it right. 33.488 units squared. We just saw that my math wasn't the greatest, but hopefully that's right. What do I report as my answer?
3.48.
Okay, 33.48. Why 33.48?
Because, actually, no, 33.4 wouldn't it?
Okay, so now you're saying 33.4. Give me a reason.
Because 4.6 only goes to the 10th.
4.6 only goes to the tenths place, so I should report to the tenths. We're going to run into a little bit of an issue there because 8 is bigger than 5, so I might end up rounding. There's a larger issue. That's wrong. What's the rule? The fewest sig figs. Does your rule set change? Yes. Which of those has the fewest sig figs? 4.6. How many sig figs does it have? 2, which means my answer is actually 33 units squared. Okay. Again, why does the rule change? We're making the assumption when we do this calculation that that is a 0, not a 9. If I make it a 9, the number comes out to be 34.1432. Where do those two numbers differ? Where do they first differ? In the ones place, which was exactly where we said we should report our answer to. Okay, that second sig fig.
Why would you not say 34 though?
Why would you not say 34? Okay. If you were 5'2", should you say you were 6 feet?
No, but if you were to argue that if you got the whole thing, are you only?
If you were 5'5", are you 6 feet?
No, but what?
If you're 5'6", you might have a better argument. 5'7". Okay. Why does your argument start to become stronger and stronger the higher that 5 foot number becomes? It starts to get closer. 33.4. Is the 4 closer to this being 33 or closer to that being 34?
Closer to
It's closer to 33, which means our answer is
So, but you're not going to
33.
8 and all in it. That's
Nope.
really looking one.
Okay, why do we not account for that? Remember, our ones place is our last sig fig. That's the last place I can report. According to our measurements, the ones place in this is then what value? Is that our observed obvious digit?
So those digits would be theoretical.
These are all theoretical. If we took our measurements to 2 sig figs, the first one is our obvious, and the next one is a guess. I can use some information about the next one to help me guess. If I continue to go out to that 8, I'm using a guess to tell me about a guess to tell me about a guess. That's a bad idea. Okay? Really what that is coming up with an excuse to guess. Okay? We want as educated a guess as possible. So we only look at that first digit. I don't care about anything
You
afterwards.
said that was 33.6, would you say that?
We will switch that around in the next example. Okay. What if? So some new addition, subtraction. Okay.
On the last one, if it was 33.5,
That's exactly what she's asking about, which is this one.
Oh.
Okay. Let's take a look at the addition, subtraction. Where can I report to? Okay. Least precise place, because it's addition, hundredth, which goes here. What's my answer become? 1.3. Okay. Well, how do I decide? Okay. This is one of those unfortunate things, because that last place, my guessing guess, okay, is right in between. So this could be 134 or 1.34 or 1.33. And because it's that 5, I'm sitting right in the middle. If it was 6, it becomes a little more obvious. Okay. So what do we decide? The way that I've ultimately decided to go through and process this ignores what the textbook says. If we are 5 or larger, you add 1. Our answer becomes 134, 1.34 grams. Okay?
Because even if that was 9, it would be 1.
So if the 5 was a 9, it's for sure closer to 3.4 than 3.3.
But it still wouldn't be 3.5.
Yeah. What happens with our multiplication division? Here's our two multipliers. We get 36.5. How many sig figs am I allowed in my answer?
2.
Okay, I'm only allowed 2 from this one, which means 1, 2. Where's the problem? That first guess. That sits dead in the middle. Let's use the same logic we used the previous one. We're just going to add 1, which means the answer becomes 37 units squared. Okay? As long as you consistently apply your rounding rules, you're fine. Okay? The biggest issue with rounding rules is, guess what? Everybody has their own set of rules. Okay? And because everybody has their own set of rules, whenever you move into a new environment, you need to reestablish what those rules are before continuing on and solving questions. Otherwise, you can end up with different answers. So you have to meet the sociocultural conventions within that system. The instant you venture outside of it, say like turn in an essay where it's a Facebook post, you're not going to get as many points because you aren't meeting the conventions of that genre. Wow, that was like 5 of those words. That was awesome. Okay, makes sense? Okay. I would argue that it is useful to have this all together on one slide. And so if you open up the slideshow, slide number 14-ish has it all on one slide. So you can print that out, you can memorize that. Anytime you do calculations, you should be using those rules. Right? What happens if you don't use those rules? You will get the question wrong. Okay? We've got some whoops, I meant to go the other direction. We've got some theoretical practice. Do you guys want to give those a swing? I heard a sure. All right. I'll give you 3 minutes. Do as many as you can. And if you got questions, raise your hand. I'll come to you. For those of you thinking it's easy, if you put down work, you'll find out you're probably doing it wrong. So the first 2 are just how many sig figs there are. Everything else is just a calculation. Three sig figs. 1, the 0, and the 2. The last 2 are placeholders, so they don't count. Question number 2, everything's a sig fig, which I believe is 6 sig figs. Okay. every single one of them because that decimal point is what identifies and keeps everything locked down. For question 3, if you enter it into your calculator, I believe you get the number 129.041 meters, which is awesome. You have proven that you can punch into a calculator. You've also proven that you don't understand sig figs and get the question wrong. What is your answer? Okay. One answer that is typically or commonly found on a multiple choice exam would be 129. Because when we go through and look at our answers, you say, well, the second one has 3 sig figs. That must be the answer, so I must report to 3 sig figs. Unfortunately, this is addition subtraction. We don't go based off the number of sig figs. We go based off of the least precise place. The least precise place is the hundredths place. My answer becomes 129.04 meters. Okay. Question number 4, we punch into the calculator, we get something along these lines. Okay. Again, you've proven your ability to punch into a calculator. That's not what this class is testing on. It's the next step, which is sig figs. Sig figs says 3 sig figs. Okay, so if we go through and underline our 3 sig figs, 4, 5, 3, notice the first insignificant digit is larger than 5, so what do I have to do? I have to add 1. Here's one of the common answers, 454 meters cubed. That's 3 sig figs, right? Okay. Best way to think about this is make this your paycheck. Okay. This was $4,538 versus $454. Did you lose meaning with the sig fig shift? Yeah, you can't lose meaning. Okay? How do we make sure that that maintains 4,540?
So would it not be appropriate to write 4,530 with a 0 and no decimal point? Because then the 0 would just be a placeholder and it could mean 8.
No, because you're now removing information from what you have. Your calculation tells you that you have an 8 there. So if you make it a 0, you're choosing to say that that 8 wasn't an 8. You're removing meaning from your calculation. So you can't make it 4530. Okay. You have to report it as 4540, right? So let's rewrite that. 4540, and now we'd be correct.
So the decimal has to be there.
But now it has 4 sig figs.
I intentionally, heavily-handedly pushed the decimal point there. How many sig figs would this now have?
4.
4. How many am I allowed to have?
3.
3. Guess what this answer is?
Wrong.
Also wrong. How do we fix it?
Erase the decimal.
Erase the decimal. That 0 is now just a placeholder telling me that I should put the 4, the 5, and the 4 in the appropriate other columns, and I now have the correct answer. Okay? Is there another way that we could write this to make it a little bit less ambiguous? Yes, and we're going to go ahead and see that in the next sequence of slides here. We're not going to look at the last 2, but I can real quickly spit out what those answers are. If you are curious, I believe it is 0.03 grams, if I did that subtraction correctly. And the bottom one, I believe, oh, that's right, I always mess that up. Liters. And the bottom one, oh, carry the 454 grams per centimeter cubed. Yeah, I'm good at math. For those of you wondering what is going on with how I could pull off that math so fast, if you and for those of you on this side that didn't see what just happened, all answers in the lower right-hand corner. Okay, I did mess up the units. How important are sig figs? If you're going to be a scientist or an engineer, sig figs are very, very important. This can be a matter of life and death. Okay? If you have to take 151 and 152, it becomes even more important because faculty in 151 and 152, like if you've heard of grammar Nazis, there are sig fig Nazis, and that is 151 and 152. Okay, so you have to be very, very careful with it. Even more so Most of those courses usually use online homework systems. Online homework systems are notoriously picky for sig figs. Okay, so you have to be very, very, very careful with how you approach sig figs. The reason why I am against it, how many different periodic tables are there out in the world? A lot. Okay? Well, at least all the information is consistent on an individual periodic table. How many sig figs in hydrogen's atomic mass?
3.
3. How many sig figs in titanium's? 4. So the sig figs aren't consistent. At least they're consistent to the same place, right? 1.01, so tenths place, 0.87, tenths place. I don't want to use these ones, but we can. I was hoping I had a different one. Oh well. God, I know there's one in there. Can't find it. Uranium. Fudge monkey. Okay, americium. 3 sig figs. Okay, and where is it precise to? Ones place. Everything's all over the map as far as sig figs coming from the periodic table. Okay, which means every time you calculate something using periodic table masses, you have to be cognizant of those sig figs. Take it a step further, you use a different periodic table. These numbers aren't exact, they're measurements. Okay? Depending on who made the measurement, they may have had a better balance, which means they have more sig figs. So depending on the source that you use, you can get rounding errors like crazy when it comes to sig figs. Okay? Only pointing that out so that you're aware of it. It is a relatively small issue within this class because it's something I watch out for very, very carefully. Okay?
So you're saying sig figs, are you saying sig figs only matter at the very end of the process? You should.
So for sure, when we look at sig figs, and this slide works, all of our sig figs have to be reported all the way through your process. Your final answer is when you deal with the dropping of significant digits, and only in your final answer. If you drop sig figs partway through your calculation, because one reported to the tenths and the other one reported to the 100,000ths place, you can't delete the 100,000ths information. That is still information that goes into your calculation. Well, your final answer has to take that into consideration. Okay? So the rounding, the sig fig rules, all of that applies at the end of a calculation, and only at the end.
It's like you have all the content, but then you
I would argue it's a hell of a lot more painful than cleaning up a draft. But yes, it is kind of like cleaning up a draft. Okay? Some mathematical simplifications so that we can get to that kind of big one. If I asked you to do this, how many of you would actually write out 4 times 4 times 4 times 4 times 4 times 4? So you would all write that out?
No.
Okay, thank you. What would you do instead?
4 to the 6.
4 to the 6th. Why?
There's less things to write.
There's less things to write. It's easier to take advantage of those exponents to help us show repeated calculations with multiplication. And for that matter, division, but the multiplication is the big one. Okay? So we can use that in our calculator. Okay? The big ones that show up, squared and cubed. Why squared and cubed? Why those terms? What does squared mean? To the second power. What is the area of a square? Length times width. If those were both measured in centimeters, this is centimeters times centimeters, a repeated calculation, and I get centimeters to the second. There's our square. Same deal for the cube. Okay? If we measure the area of a cube, length, width, height, that's why we're cubing. Okay? So you may hear reference to squared and cubed. Okay? The next one is our powers of 10. Okay? Powers of 10 allow us to scale numbers outside of the realm of human comprehension. Okay? So if we looked at, say, our national debt, most people are like, it's not that big of a deal. Okay? Until you actually process what trillion means. Okay? We might, and I'm not even sure I'm right. What is it? Anybody know? $20 trillion. Well, 20. You know, I just go into the bank and I get out a 20. It's not that big a deal. I get it all the time. And then we process what trillion means. What is the point of using trillion? The point of using trillion is so that we, as our horrible human brains do, remove all of those millions or trillions of zeros to make the number make sense in our brain, okay, to scale it. We're doing that with powers of 10. We can use powers of 10 to confuse the populace, to make them accept national debt. Okay? We can also do it to scale up something that's so incredibly small up to a system that allows us to actually understand and somewhat wrap our heads around. Okay, so it's a scaling factor. Okay? When we do it with scientific notation, it can really help us out. Okay? With that measurement that we had before, okay, what was our measurement? Everybody remember? 4540. And that 0 was not significant. I only wanted 3 sig figs. Okay? I've talked to plenty of colleagues who say, well, that's ambiguous. You have to be more careful with it. It's not freaking ambiguous that 0 is not significant. Okay? If you want to be extra clear in your explanation that that 0 is not significant, we can convert this to scientific notation. Scientific notation says the very first significant digit goes into the ones place. So the number becomes 4 decimal point 54. And now I just write out all my significant digits. Because the 0 is not significant, I don't list it. Cool. That worked out really nicely. Okay? Except my paycheck went from $4,540 to $4.54. When I do my conversion, I want to make darn sure I don't lose meaning. How do I avoid the loss of meaning? Multiply by the power of 10. Okay? What power should I multiply by? We'll go back to your starting number and say, how far did I shift the decimal? Remember, there's an implied decimal there. How did I go? 1, 2, 3 places. So this becomes 4.54 times 10 to the third. Positive or negative? Okay? It's positive. What you'll hear a lot of people say, oh, you shifted the decimal to the left or to the right. Okay? Depending on which way you're converting this, you're shifting the decimal different directions. So this, oh, shift left or right definition does not work consistently. Okay? Look at your number. Is that a big number or a small number? Big. Guess what the sign needs to be? Positive. Okay? Next example, real quickly, because we're almost out of, well, yeah, it's because we're almost out of time. Number above. I went through and took this measurement, but I measured it by 1,000 meters. Okay? So I have a 1,000-meter stick, and I took this measurement. How many sig figs do I have?
544.
I agree, all of those are sig figs. I would also agree these two are sig figs. Why? What did I use as my measuring device? 1,000-meter stick. Okay? If I took a measurement at the 1,000-meter mark, I would know that that is a 0, a 1, 2, 3, 4, 5, 6, 7, 8, or 9. So I actually have those two zeros also being significant. Does my measurement as written show those zeros as significant? No, it's too confusing. How can I change my measurement so now everybody knows those zeros are significant? 4.06300 times 10 to the, how far did I shift my decimal? 1, 2, 3, 4, 5, 6, 7, 8. That number is really big, so my number needs to be positive. And I now have a way to take that measurement into consideration. Okay? Just to real quickly end this, the one below it becomes 1.16 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8. I went 8 places again. Is that number big or small? Small minus